Hi boys and girls, Varsha and Vidya. In the last presentations, I told you about the use of PN sequences in spread spectrum communication, both with direct sequence spread spectra as well as with frequency hopping. Today we will see how these pseudo noise sequences, especially the M sequences, are generated. So let me start with that presentation. What you will learn in this short video are that you will learn the generation of maximal length PN sequence or M sequences. Then you will learn the properties of M sequences, especially the correlation property, the autocorrelation, cross correlation of M sequences. And then you will understand some limitations of M sequences, and you will learn how to derive gold code from M sequences. So maximal length sequences, all sequences are generated with the help of shift registers, and shift registers are but delay flip-flops connected together with a common clock. So with some feedback mechanism, with some logic circuit, here it is a modulo 2 addition. Now this generation of PN sequences that relies on irreducible polynomials, here if you see the polynomial is PD, that is D7 plus D3 plus 1. This is my shift register, this D1, D2, D3, D4, D5, D6, D7, this 7 delay flip-flops are there. So this delayed value D7 and D3, they are added, which is nothing but an exclusive OR operation. This is a binary addition. Then it's added to the input, making this D7 plus D3 plus 1, that is my PD. And these flip-flops are driven by a common clock. This PN sequence comes out of this. So you can have many such irreducible polynomials. You may refer the book Communication Systems by Simon Haken for similar codes or similar irreducible polynomials. You can run Python on, you can use Python and create many such codes and understand the properties. And when you come to the properties of the M sequences, you can see that the number of ones in an M sequence is one more than the number of zeros. If you come here, this is a seventh order one. So this length of the PN sequence is 2 raised to 7 minus 1. So that is 127. In that code, if you look, the number of ones is one more than the number of zeros. And if you look at the number of runs of zeros and 1, you can see that the number of runs of single 1 or a single 0, that is 1/2 the length of the code. Say for example, if you look at this 32-bit code, here if you count here 1, 2, 3, etc., how many ones are there? There are 16 ones, that is half of 32. And if you look at the runs of pairs, like let us look for the pairs of 1. This is not a pair, this is not a pair. Here I see a pair, that's 1. This is another pair, 2, then 3, 4, 5, then 6, 7 and 8. Now that is 32 by 4. Okay, 32 by 4, that is 8. There are 8 pairs, and if you see the quads, you can see that there's there is two quads are there. 1, 2, 3, 4. There's a 1, 2, 3, 4. Okay, there are there are two of them. Okay, there is nothing but 32 by 2 raised to 4. That is 32 by 16. That is two quads are there. So and when it comes to the correlation, the autocorrelation function of the sequence is very important, meaning that if you use an M sequence, the correlation of an M sequence with itself should be very high. That's the autocorrelation should be very high, and the cross correlation between two M sequences should be very small. Why? Because your transmitter transmits at a time using a certain PN sequence. Only the intended receiver has that PN sequence. So the correlation between the transmitter and the intended receiver should be very high, and any other receiver in the vicinity should not have this PN sequence. It may be having another PN sequence. So the correlation between that receiver and my transmitter should be very small, so that the second receiver or an enemy receiver should not receive that. So if the cross correlation is if it is not very small, then that enemy receiver can also receive mean. So it is strongly recommended that the autocorrelation value should be very high and the cross correlation should be very small. So this function is the autocorrelation Rx0 is 1 and Rx tau not equal to 0, that is a minus 1 by n, and this value should be very small, and the cross correlation between two sequences should also be very small. And when I look at these properties, I will run a Python code and we will analyze the properties. If you come here, look at this thing called PN sequence. This actually simulates a 2 raised to 7 minus 1 length code. This is a 127 long code, and this loop simulates the feedback and the shift register. And this PNS, this two times RAPN minus 1, that makes it a what you call a bipolar type PN code or M sequence. So this one, then I have to compute the cross correlation between the PN sequence and itself. That I do with the help of the scipy.signal module, sig.correlate, pns.pns computes the correlation, and we plot that. Now if you run this code, we can see that if I run we can see the code from here to here. There is some 0 to 127. Okay, if you go here, it's a 127 bit long code. Okay, there's not much, not anything intuitive in this code, but if you look at the correlation value, you can understand many things from that. If you look at the middle of the value, this is nothing but my Rx0. Rx0 is quite very high. That value alone, that is very high, and this is actually Rx0 because there's a 128 long code, 127 long code, and it's a correlation with itself. So that is this sequence has a length 127, and this comes at the middle. This is actually the zeroth value. This is actually the zeroth value. That is Rx0 is very high. Okay, this is not a normalized thing. This correlation is not normalized. That's why you get a value 120. Here it is 125 rather than a unity. It should be 128 or 127 actually. This peak should be 127 because the length is 127. So if we normalize by the length, it will come to 1. But this is an unnormalized. This curve is not normalized. And if you see other values of Rx tau, they are very small. Some are typically negative, some goes high. So this is how the autocorrelation function of an M sequence looks like. And then there is another code in which last time I gave this as a laboratory experiments in the communication lab, and they actually made a 2 raised to 7 minus 1 M sequence with the help of shift registers, I think 7495 ICs. And they captured this M sequence on a digital storage oscilloscope, and they saved it into a pen drive. So this is a value msec2.csv. It's a sequence captured on the this CSV file captures PN sequence. So the first column, that is a time axis, the time base of the CRO, and the second one, that is voltage of the voltage output of the IC output, that is M sequence voltage value. And I use pandas for reading this thing, and if I run this code, run msec, you can see that this is my this is my M sequence. If you zoom this, you can see how the electrical waveform, corresponding electrical waveform looks like. And this is a correlation value. You can see that middle value of the correlation, that is high enough, but there are some other components also. I'm not exactly sure about the validity of this code. but it gives you a feel of the electrical signal corresponding to the code. When I come back to this presentation, this autocorrelation should be very high and the cross correlation should be very small. But M sequences typically have a cross correlation of around 40, but normal CDMA systems require that the cross correlation should be much smaller than that. So what one can do is you can have a combination of the two M sequences to form something called a gold sequence. This is one typical arrangement. You can see that this is one M sequence generator and this another M sequence generator. This relies on the polynomial D7 plus D4 plus 1, and this uses a irreducible polynomial D7 plus D6 plus D5 plus D4 plus 1. Okay, these two M sequences do come here. They are XORed together to form something called a gold sequence. These gold sequences are very popular in CDMA systems. The gold sequences have a cross correlation below 70, typically 15, etc., which is good enough compared to the 40 of the M sequence. This is how you create a gold sequence. And what you understood in this thing, you learned the generation of maximal length the PN sequence, and you learned the properties of PN sequence, especially the correlation properties. You simulated the correlation property with Python, and then you understood the limitation of M sequence, namely the high cross correlation values, and you learned to derive a gold code from M sequences. That is the end of this presentation, and that's actually the end of this module as well. I thank you all.